So let's look at our list of slides. Before you throw the ball, the algebraic schemes for a base field, those are the ones we are studying, not any random schemes. So of course, a whole lot of you are interested in number theory. And you are interested in doing stuff not over a base field but over, say, a ring of integers. How about over Z itself? You want more general category of schemes to do your intersection theory. But that will come later. It's always easy to first study things over a base field. Even easier to study them over an algebraically closed base field. So far we are not, well, so far something not being algebraically closed came up only once in that ad hoc proof that A0 of An is 0. There it came up because the residual field might have been an extension. That complication wouldn't have arisen if K was algebraically closed. Sometimes field being algebraically closed is useful, but otherwise a random field is okay for most of this. Sometimes a perfect field is needed, etc. And then for such schemes we define Chow groups. A homology theory also serves as a cohomology theory because sometimes there is pullback. So homology / cohomology theory, for which the cycles came from algebraic subvarieties. Okay, this is its connection with visual geometry. Cycles are subvarieties. Okay, and their formal linear combinations. And then we kept tab of closed subvarieties in terms of generic points, whatnot. But in order to define when is one cycle equivalent to another, we brought up the notion of rational equivalence. And this rational equivalence led to Weyl divisors in terms of where that rational function on a variety has its zeros and poles and how much, what's the multiplicity of the zero. Okay? So that's why we needed an idea of order of vanishing or pole. This we modeled after discrete valuation ring, but we gave an alternative description of it that even over discrete valuation ring, this is simply the length of something, of a finite module. And that length definition generalized to Noetherian local domains of dimension 1 when you are going modulo something non-zero. It further generalized, later on we needed it, to Noetherian local rings, not necessarily domains, of dimension 1 when you are going modulo something which this time is not just not zero but is a non-zero divisor. And Noetherian remained important for this because only because it's a Noetherian dimension 0 it's Artinian, so there is length. And moreover, if you want to go modulo non-zero divisors, you need a good control on non-zero divisors, which is possible on Noetherian rings through the theory of associated primes. Okay, let's go on. So once we manage that order of 0 or pole, we could define the Weyl divisor and we defined rational equivalence. Two cycles are rational equivalent if their difference is a linear combination, formal sum, subtraction, whatever, integer coefficients of Weyl divisors. And so we arrived at Chow groups. This was lecture number 1. With all this, repetition is very important. As I keep telling you, in any exercise, in mastering any skill, there's nothing like practice. And so there's this joke that, oh, what is the way going to NCPA? So the answer is via practice. Okay. So you get invited to perform in the National Center for Performing Arts, play your violin or sing your khayal or what it is, and the road there goes via practice. Okay, so you have to keep practicing what you have learned, and therefore in the evening I hope you look at the day's lecture notes, lectures, whatever, and go through it once again and digest it, talk with each other about it, discuss with each other. I told you guys to discuss with each other the stuff, and let me remind you that you are going to be each other's colleagues for the next 40-50 years and research collaborators and so on. So these workshops are the opportunity when you seriously get engaged with each other and learn the art of collaborating instead of some kind of insecure competition oh, I don't want to open my mouth and appear a fool in front of somebody. That kind of competition you give up, you learn the meaning of team spirit and you learn to admire your friends. Admiration is the greatest antidote to jealousy. I'm not saying you're suffering from jealousy, but just remember this sentence. Okay, so I hope you are doing it. All of you are talking mathematics, talking this stuff, and also talking all other non-mathematical things. So are we. So yeah, for your faculty of any workshop, it's a great opportunity to meet their colleagues and even learn new things from students. Yeah. So then, having defined Chow groups, we checked various simple properties of Chow groups, Chow group and dimension, what happens in affine line, what happens in affine space, where we don't know about only 0 and top. Projective line we evaluated, and there the degree played a role. Degree gave an isomorphism between the 0th Chow group of projective line and Z. And then we introduced the all-important notion of degree of a proper surjective morphism of varieties. And I motivated degree for you in many ways. This is the amount of how much it wraps. Okay. In topology, if you have continuous map, sometimes this wrapping turns back. Okay. So here's a line, oriented as I said. Here's a second oriented line. And this is the projection. What is the degree? What's the degree? Huh? This goes to infinity all the way, Is this map proper? What's the inverse image of a compact set? Compact. Okay. This map is proper. These are Hausdorff locally compact spaces. So this is a proper map. Over a general point, how many points are there? 1. And what about this point? There are lots of such points. An open set full of such points. Over which there are how many points? 3. But the orientation is reversed for one of them. Right? This point, it's going forward where this orientation is going, but here the orientation is backwards and here the orientation is forward. So if you take the weighted sum, that weighted sum is going to be 1. So in topology, where you are taking proper maps of oriented manifolds, the map need not be orientation preserving even at points where the Jacobian is non-zero. So there you have to take care of the degree by taking weighted sums of the points. What about the other definition, Dirham cohomology, whatnot, pullback, what will happen? So I'll take a little bump function here and I'm going to integrate this bump function as fx dx. This bump function I'll pull back to a bump function here, bump function here, bump function here. So integral of this is going to be integral of this, integral of this, integrals, except that this dx, here is dx, there it is minus, and there it is again plus. And so this integral is going to be minus of this integral, cancelling it, giving you 1. So these local neighborhoods are going down correctly, and this integral with correct orientation is this integral is called what? Change of variable formula for integration, in which the determinant Jacobian comes. Yeah? And then when somebody asks me what is the degree of a map from P1 to P1 in terms of Dirham cohomology, where's the guy who asked? There. Huh? I said, yeah, how many points count? And at that point, I forgot to add that when you have holomorphic map, and if its derivative is non-zero, then the Jacobian is the absolute value square of the derivative. This you know from Cauchy-Riemann equations. And being absolute value square, if it's non-zero, it's positive. So a holomorphic map, if it is Jacobian is non-zero, is necessarily orientation preserving. Therefore, only +1 is counted every time. No question of -1 arises. Okay? You followed this? Okay. I will take every opportunity to digress from what I am talking about, because you already have it in various forms in your hand. Because all of this is connected to lots of other things, and you have to see mathematics as an integrated whole as much as possible. Not all of you are going to become specialists of algebraic cycles. You want to deploy algebraic cycles in something else which interests you and apply it there. And so it always helps to connect it with other things and not keep it in one very narrow specialization. The danger in commutative algebra often becomes that because commutative algebra can be studied in a very self-sufficient manner. But then that becomes a prison finally. Okay? So always take every opportunity to break out of your narrow specialization. Alright, so that was the idea of degree of a proper surjective morphism. This line led to all such digression. So once we had the degree of a proper surjective morphism, which we could define the proper push forward of cycles. If the dimension was decreasing, the push forward was defined as 0. And if the dimension was the same, so and being proper, therefore it's a proper surjective morphism of varieties of the same dimension, such a thing at the level of function fields is a finite extension. Same transcendence degree because of dimension, and a map is induced because the generic point is going to generic point. So I have two finitely generated field extensions of K and they are the same transcendence degree, and one is the extension of the other. So because they are the same transcendence degree, this is a finitely generated algebraic extension and therefore a finite extension. This is why the degree is finite. Okay? I had not mentioned this because, well, but did you ask this to yourself and figure it out? Very good. And did you share this interesting observation at breakfast saying, hey, you know that, never mentioned, but I have figured it out. This is the kind of way you have to share with enthusiasm your new knowledge. You begin sharing your new knowledge with enthusiasm with your friends, and in return they'll share something with you. You'll see. So you have to open discussion among yourselves. Perhaps you already do all this and I'm preaching to the converted. Then pardon me. Okay. So there goes proper push forward of cycle. In different countries, the culture is very different. In England, if there is a classroom, and if this was a classroom in any of the top Oxford, Cambridge kind of places, and some advanced lecture going on, and there are 10 students, where will they sit? You know, one here, one here, one there, one there, one there, one there, and they'll not even look at each other. They have not been introduced, perhaps. I don't know. I have seen this first and I was pretty surprised. In India, at least they sit close, whether they discuss mathematics or not, I don't know. So we defined push forward of primitive class, the cycle of an irreducible variety by multiplying by the degree. You can write it as a combined formula by declaring the degree to be 0 if the dimension decreases. Artificial definition, but it saves them making cases. So now if you want to show that this homology theory defined in terms of cycles which come from varieties goes down to Chow groups, then you have to show that rational equivalence is preserved by this proper push forward. And for that our tool was basically rational equivalence is generated by Weyl groups of single rational functions on algebraic varieties. And under equidimensional case, I want to know what happens under this map. And then we showed that that thing becomes the Weyl divisor of the norm under that finite field extension. And therefore it remains a Weyl divisor, therefore it's rationally equivalent to 0. Therefore rational equivalence is preserved. That's how it went down to Weyl groups. Sorry, to Chow groups. So this was working out the details. This lecture was telling you that how that happens. In relative dimension, this happens, that happens, because there's an added complication. I may have variety, I may have another variety, and it may be of even one dimension less. But the Weyl divisor involves codimension 1 varieties here, which might be mapping to all of it. That's not ruled out. So in that case, just because that codomain variety is smaller dimension doesn't mean that the Weyl divisor is automatically going to go to 0. There's work to be done. Okay. There's the other case, simpler, where they are same dimension and these also go to same dimensional stuff. Then it's a finite morphism at the generic point of that closed subvariety downstairs. Okay. So we made various such cases dimension wise and proved this. This was lecture number 3. You remember this? Okay. By the way, it's a lot to learn in 1 week. I certainly did not learn this material in 1 week, or 1 month, or 1 year even. Okay, so what does it matter? So you have to go on thinking about it. So after doing all that push forward, then we began on pullback via flat morphisms. Straight away, we encountered the following problem with flat morphisms. One could define what to do with cycles, because one could define what to do with a closed subvariety. Just take its inverse image. But it's not a subvariety. No big deal, because any closed subscheme has its fundamental cycle. Take its highest dimensional irreducible components, look at their multiplicities and sum up. Forget the other dimensional ones. And if your morphism is flat of constant relative dimension, which is what we need for all the techniques to work here, then they are only the top dimensional components, and then you can write what is the inverse image of square bracket V. Alright, so at the level of cycles we have it, and there's a little bit to be proved there, that pullback of pullback is pullback by the composite, which is certainly true for the subschemes themselves. So there's a little bit of work to be done, which we did, and showed that, yeah, there's a well-defined pullback homomorphism at the level of cycles. But we want it at the level of Chow groups. So we want to be able to pull back rational equivalence. Now we are face to face with the real difficulty, that I have rational function of variety, I pull it back, the variety, it's a scheme, not a variety necessarily. So what do I mean even by a rational function there? Can I pull this rational function back there to something meaningful? And my answer to that, this is not the path which Fulton's book follows. My answer to that is yes, expand the idea in a well-known way, which is there in the literature, unfortunately not explained in textbooks, of defining meromorphic functions on locally Noetherian schemes. Meromorphic functions can be defined on locally Noetherian schemes, generalizing the idea of rational functions on integral schemes. And the idea is to take ratios f upon g as before, but this time instead of just saying that g is non-zero, you want g to be a non-zero divisor. Otherwise the problem comes f upon g is equal to fh upon gh, and gh might be 0, so you are left with a 0 denominator. Okay? So one can successfully extend the theory of rational functions and their germs and all such stuff to locally Noetherian schemes. This is done in excruciating detail in the first chapter of my notes. Okay? So go read it. And again, in order to handle non-zero divisors, which is the one by which you divide, you need a good grip on non-zero divisors. That comes because of the theory of associated primes. And flatness becomes very important because a flat homomorphism of rings sends non-zero divisors to non-zero divisors, because scalar multiplication by something is an injective map is the same as it's a non-zero divisor, and so under base change it's scalar multiplication by the image of that element which is injective, therefore it's a non-zero divisor there. Yeah? Am I saying all this too fast? Let me confess, it would have been too fast for me if I was in your place. But then I think, and assuming of course that I can explain things well, let's assume, then I have an explanation. If the hypothesis is false, then I have to forget the explanation. But my explanation is very simple. I don't understand easily. And I have some 5-6 different questions to a simplest statement. But. And because I don't understand easily and I am deficient in common sense and all the standard assumptions that one would automatically make, because I am deficient, when I have to explain it to people, I put in all those little things which to somebody more talented would have been automatic. Won't even think about it and will say, of course, of course. If you ask, he will go back and answer that, but by himself, such a person will not even mention it. I know this, I have seen it repeatedly. Okay? So I have some very good mathematician colleagues whom I greatly respect, far more talented than me. My problem with them, one of the problems is if I ask them a difficulty, the answer is so fast that I have to all the time apply a break. Now I am pretty shameless, and so I can apply the break and say, please, I don't understand, can you tell again? And tomorrow I go back and say, no, yesterday I thought I understood, but can you once again tell me? Do you guys do this? then you have to keep apart fear, ego, all such things. Then you can do this, go and again ask. Do it, try it, it's fun. Okay, so coming back to this, how flat pullback of cycles preserves rational equivalence. So I have a Weyl divisor on a variety there. I pull back the variety, I get a scheme. I pull back the rational function, I get a meromorphic function. And now my job becomes showing that pulling back of meromorphic functions and then taking Weyl divisors commutes with first taking the Weyl divisor and then pulling back the Weyl divisor. This is where my second observation, which again Fulton did not have. In order to prepare these lectures, it dawned on me that, hey, all these are sheaves. Then why don't the experts write it in the first chapter, these are sheaves? Anyway, so the cycles form sheaves. Meromorphic functions obviously form sheaves. So such a commutative diagram, which is happening between sheaves, because the maps are defined globally, I only have to check the commutativity locally. And so I can go to algebra and check the commutativity on affine open curves. That's how I did it. And I proved that pull back a meromorphic function and take the Weyl divisor is the same as take the Weyl divisor and pull back for flat morphisms of constant relative dimensions between schemes. So I realized that there is a certain Grothendieck topology, the big Zariski topology, on which cycles form sheaves. Big Zariski topology on schemes with flat morphisms of constant relative dimensions, and then on that this commutative diagram also works. So I am not saying such words here, but so that what will exactly tell you that why you can base change and what not. There are topological quote-unquote spaces which are spread over all schemes. And this is really happening in one such called the site, the big Zariski site of finite type schemes over K. And so this commutativity is finally a little bit of algebra that I have to do. And that's done in the notes that I'll again do on the slides. So this is why pullback commutes with Weyl divisors and therefore rational equivalence is preserved, which is what we wanted. Pullback of rational equivalence will be. Hence, the pullback homomorphism on the level of algebraic cycles descends to a pullback homomorphism at the level of Chow groups. So these are the two functorial properties. But so this is what it is up to now. Any questions on this? None. Great. So today I am going to do these things. I am going to say that the Weyl divisor lies in rat in. So you see, the pullback of the Weyl divisor, I said, pullback of the Weyl divisor of a rational function to that scheme is the Weyl divisor of the meromorphic function. But remember, we only declared Weyl divisors of rational functions and their linear combinations to be 0. We have not declared the Weyl divisors of meromorphic functions on schemes to be 0. What was our definition of Chow group? Chow group was taking algebraic cycles and going modulo linear combinations of Weyl divisors on varieties of rational functions on varieties. So my proving this commutativity still leaves the question open. Okay, you have shown that pullback of Weyl divisor, but why is this Weyl divisor a linear combination of Weyl divisors of rational functions on varieties? Only then you can say it's 0. Got the point? That's what I have to do then. So that is the first slide and second slide. And then, well, pullback of Weyl divisors, how it is done, and completing the proof for flat pullbacks. That's what I am going to do today. So just now it's 10 o'clock, maybe by 10:30 or so I might be done with this. And then we'll begin on this stuff. This stuff begins, this addresses the question, there is proper push forward. There is flat pullback of constant relative dimension. How do these interrelate? After all, I might have some flat morphism to X and some proper morphism here. Then I might take a Hilbert square, and then that will be proper, this will be flat. And now I can go here to here by first pushing proper push forward and then flat pull back, or first flat pull back and then proper push forward. Will I get the same thing? This is important, because then all kinds of things will become simple. Okay? And it is indeed so. And this push is proper push forward, and pull is flat pullback of constant relative dimension. And push pull is pull push means pull composite push is push composite pull. Yeah? So you see why such a result is important. It immediately strikes you that this should be, if this is so, this must be nice. Right? It should immediately strike so. Of course, not everything commutes. And this is a true story. TIFR had an IS officer assigned by DAE, and the question came 1 year of justifying our funding, and then there were things being done which were non-commutative. So the IS officer wanted to know, what is this non-commutative? So I said, see, you first wear your socks and then wear your shoes. The result is pretty different from first wear shoes and then wear socks. She said, yeah, can I write it in the planning commission report? I said, so you see, when things don't compute, it's even more interesting, apparently. All right, but suppose things commuted. Then your dressing up in the morning will become very easy, na? Wear your things in any order. There's nothing like first wear this and then wear that. Okay? See how commutativity would have been useful. Sorry, I have to entertain myself giving the talk. So this is practical aspects of commutativity. Commutativity is very useful when it is there. For example, there is something called abelian signed pile. But let me not say anything. Its practical use is to generate hundreds of research papers. Okay, because it's abelian, it works. So, after doing this push, pull, pull, push, etc. business, we'll come to another topic, and this is very important. Suppose I have one thing open and its complement which is closed. In singular homology, etc., you have that sequence of pair and whatnot, all kinds of things. Okay, so we'll come to that. It tells you how the Chow group of an open subscheme and that of its complementary closed subset are related to the original Chow group. By the way, you must have realized by now, and if I have not made this comment explicit, let me make it explicitly now and treat it as an exercise. Suppose I have a scheme which for us are algebraic schemes over K, and take its Chow group. Now take the underlying reduced scheme and take its Chow group. How do you think these two compare? What do you say? And how will you compare them? Second. So you see any proper morphism? The underlying reduced scheme is a closed subscheme of the scheme, right? So it's a closed embedding. That's a proper morphism. So now can you make a precise statement referring to this proper morphism? What happens to Chow groups under proper morphisms? Push forward. So there is an obvious homomorphism graded degree 0 between the Chow groups of the reduced scheme and Chow groups of the original scheme. So any guess? Guess. What will you think of? What will happen with cycles? Any closed subvariety of the big scheme already exactly same as good. So cycles are going to be the same, yeah? Where is rational equivalence going to come from? Such closed subvarieties which are already in this. So what's the conclusion? The Chow groups do not see the thickness of the scheme at all. The Chow group only sees the reduced scheme. But all the intermediate stages, morphisms, whatnot, heavily use the non-reduced structure, which matters. Okay? Thickness matters all the time, length, etc. Okay? Fundamental cycle depends on what is the geometric multiplicity of the components. So think about it. So you had not noticed this probably. Nobody had thought in his mind that, oh, I can have reduced schemes always, and then what will be the chow group? Yeah? So write down the proof of this in your own words, that the inclusion of a reduced subscheme of any scheme which is proper, verify that, induces isomorphism on chow groups. It's tautologically true almost, but then it becomes a bit baffling. So think about it till you get comfortable. Okay, so that open subscheme has a closed complement, and I don't have to say what scheme structure I give it. Give it the whatever scheme structure, the closed subscheme structure. The chow groups are going to be the same, because whatever closed subscheme I give to it, the underlying reduced scheme will induce an isomorphism. You give any two different ones, they may not be each other's closed subschemes, but the underlying reduced closed subscheme will be a closed subscheme of both. So what kind of thickness I give to the complement of x minus u, I can leave unsaid, or you can by default always say take reduced. Yeah? So then how is it related? And the answer to that is a certain right exact sequence. It's not exact on the left, and there opens a big area of research that how to complete it and what do you get there. Those are called higher chow groups. And what are they exactly, and what are their properties, and what not. All this is still a subject of ongoing research. And then we come to tomorrow's lecture, which will talk of Cartier divisors. I could have fast forwarded it since people needed Cartier divisors, restriction of Cartier divisors. Or by then I won't have to say anything about it, because Amit might have done everything that I would have otherwise said. Then I'll talk of Noetherian induction. I found, again to my surprise, that, or rather I couldn't find any nice account of Noetherian induction. Noetherian induction is used by all algebraic geometers, all commutative algebraists, and there should be some nice, like in school you have this account of piano induction, Pn implies Pn plus 1 and P0 then all, and so on. So I have written a slide of Noetherian induction. So it has nothing to do with algebraic geometry. And then we'll use it to address the cohomology of affine bundles, which is something again Amit might have finished doing by the time I come there.
Yeah.
Wonderful. And then I will talk of chow groups of affine and projective spaces. Again, something he will do, and I'll be saved talking about this. And so really, I will spend time doing my additional material, which is rational equivalence via morphisms to P1, and which allows me to prove the universal property of chow groups. So all this is going to happen tomorrow in my last lecture. All right. So there is a bit of algebra involved in doing this. So suppose I have Noetherian local ring of dimension 1 and I have some non-zero divisor. A non-zero divisor, as I told you, goes and cuts each one of those minimal primes. Its vanishing locus cannot contain any prime, because the union of associated primes are the zero divisors, and minimal primes are always associated primes. Plus the maximum ideal could be, may not be. So if these are the minimal primes, and I am going to go modulo this A, and this is my notation, A, P are the localizations at that P, and this is the cut of that component by A, okay? Then these are all Artinian, because I chose A to be here. So this A is not in this Pi, this A mod Pi is one-dimensional domain, and now you are going by something non-zero. So it's becoming Artinian. And then the length of this is going to be the sum of the length of A Pi, means how thick is that component, times how much this AI vanishes on that domain. That thin component, how much it vanishes on that, times the thickness of this, is the total amount of vanishing of A. Make sense? Justice, this is how it should be, but then one has to prove it. And so I have written the detailed proof in my notes. That is statement 2.28. Lemma is in full turn. So A whole lot of this algebra which you will find in my notes is expanded from the somewhat telegraphic proofs written in Fulton's appendix. Fulton's book has an appendix on algebra. So many of those proofs and arguments there were too short for me to understand, so I had to struggle with some of them, and so I wrote longer proofs which even I can understand. That's why the proofs are that long. So by definition of order, once I prove this, this is the order of vanishing of A. This is the order of vanishing of AI restricted to that irreducible component. And this is the thickness of the component. So this is the equality we have. This equality is for A coming from here. Okay? But I can extend this equality to the total quotient ring also. How to extend it? Because I cannot go modulo a meromorphic function here. Meromorphic function is not an element of A. So it cannot have the same explanation that go modulo it and look at the length. So I have to do it separately for numerator and denominator and subtract the two resulting equalities, because if indeed A is a non-zero divisor, and if I take the product of two non-zero divisors, then it is additive. So on ratios, the subtraction is well defined. Okay? If A upon B is the same as AC upon BC, then what you get on AC subtract what you get on BC, and because both are additive, the contribution of C will cancel from the plus and minus side. And so you will get a well-defined thing on the ratio. So this is how it is done, A upon B. So by subtracting this, you get this answer. Okay? Where what is the Ri? So if Ri is Ai upon Bi in this is really a field. So that was this slide. Any questions on this slide? 5.1 is done. Any questions? So what is 5.1 devoted to? It is devoted to talking about the order of a rational function, order of vanishing of a rational function on a one-dimensional Noetherian local ring, which is not necessarily a domain. How did we accomplish it? We looked at its minimal primes and went to those individual varieties A mod Pi, and there we knew how to do things, and we knew that A cannot be in any one of these, being a non-zero divisor, and so those cuts always gave you Artin local rings, and everything was therefore defined. Okay? So yeah, you have to stare at these statements till they start making sense. Try to write the proof yourself, get stuck if you indeed get stuck, and then only then look at the proofs given, and then again go back and so on. What I have been telling you, that kind of repeated exercise. So now we are going to apply that algebraic lemma to a proposition, to writing the Weyl divisor of an invertible meromorphic function on an equidimensional algebraic scheme. So I say invertible, so you remember my yesterday's comment. Over a field you talk of matrices, you say determinant non-zero. Over a ring you talk of matrices, you want the general linear group, you say determinant invertible. Always invertible is how you generalize non-zero. I shouldn't say always, there may be some other context, but in this context at least. So we are going to apply that formula. I have an equidimensional scheme of dimension n plus 1, and I take a particular closed subvariety V of dimension n. Why did I take a closed subvariety of dimension n? Because those are the ones which are going to occur in any n cycle, linear combination of closed subvarieties. And so to understand what is this n cycle, I need to know what is the numerical multiplier of any such V. So I take one such V and focus there. How do I focus at anything? I localize there. I go to its generic point and look at the local ring. Right? That's how you do. You have a scheme and I have a closed subvariety, and I am interested in what's happening on this closed subvariety, at least generically. So I go to the generic point and localize, and I have a local ring, and that's where things are happening near it. So we apply the above thing to the ring localization of X at this V, and the germ of R, which I'll again denote by R, not too much notation. And the Xi's that contain V, you know, the irreducible components of X that contain V, are going to correspond to minimal primes Pi in this ring. No, So there was this funny scheme which had lots of irreducible components. They had different thicknesses and whatnot. And there was this sub-variety of dimension 1 less. Because it's a variety, I am drawing it very thin, no thickness. And it's dimension 1 less, so because this I have drawn as something one-dimensional, that is a point, 0-dimensional. And there the local ring is this one-dimensional Noetherian local ring. Okay. So now I want to know what's happening around here, which means some kind of smaller and smaller neighborhoods maybe. So functions defined in smaller and smaller neighborhoods. How do you study geometry algebraically? Well, in terms of functions. I am interested there, so where should the function be defined? In any neighborhood. What if I take a smaller neighborhood? Even better. But then what about my earlier function in the larger neighborhood and this new function in the smaller neighborhood? Well, if they are equal in an even smaller neighborhood, we'll treat them as equal. What does this definition lead to? The definition of a stock, right? So when you want to focus attention at a point and study what's happening around in terms of functions, you have to study equivalence classes of functions. Two functions are equivalent if they are in a tiny neighborhood, same. For example, you study derivatives, right? Take derivative. Now, do you need a whole function to take derivative at, say, origin? No, you need it in a small neighborhood. You're after all going to take f of x plus epsilon minus fx divided by epsilon. Epsilon is small. What if I give you the function in an even smaller neighborhood? Good enough. What if I restrict that function to an even smaller neighborhood of 0? Still you get the same derivative. So what really matters is how the function behaves in smaller and smaller neighborhoods. But that's the germ of the function. That's the stock of the sheaf of differentiable functions. So that's why you go to localization. You understand why all the time we are going to localization? Because we want to know the behavior around there. And for that, functions don't have to be everywhere. And two functions which are equal in a small neighborhood are to be treated as equal. That's why we are all the time going to local rings. Yeah? Geometric explanation. So we are going to go to this local ring of smaller and smaller and smaller. And that's this one-dimensional thing. And that is the one in which suddenly this point starts looking like M. And this thing starts looking like Pi, Pj, etc. And we are back in the picture of a Noetherian one-dimensional local ring. And then I am going to have some invertible rational function and it's going to cut something. And that cut in this is going to appear like that element A of that previous thing. So you see how that algebra directly allows you to do the calculation to find out the numerical coefficient of phi. The left-hand side of that proposition is going to give you the numerical coefficient. This is the numerical coefficient you want of the variety, and this is how it's going to look in terms of its restrictions. Why am I interested in how it looks in terms of restrictions? Because after all, I want to express it as a rational, as a weight divisor of rational functions on varieties. So I want to think of varieties, and those varieties are the reduced ones all the time. Okay, so A mod Pi's are going to be those varieties, and those Ai's, A restricted there, is a rational function on the variety, and its weight divisor on that is going to contribute the right hand side, and it's going to get this numerical coefficient, which is a certain thickness of that. So you understand, geometrically you understand why I must have such a formula and how it translates into geometry. Why this is the kind of formula I need if I want to do the geometric calculation. So this is often more important. And again, my complaint, but then I am an outsider to mathematics, almost I am a physicist, is mathematicians don't explain this. They write books like fat, definition, theorem, proof, why they are doing this, where they are going, where have they already come, and what is skillfully left unanswered is also left unasked. They don't say that we have proved this, but what we would have really liked to know is what is this, but since we don't have result about it, we have kept mum about it. If they write this, it will be self-contradictory but very illuminating, right? But they are more bothered about consistency, so they don't say this. I am not raising this question because I don't know the answer. If they say that, I am not raising the following question in my paper, blah, blah, blah. The reason I am not raising it is because I don't know the answer. In fact, I am working on it every night and hope to complete the proof before anybody more clever than me with a sudden bright idea completes it. Therefore, I will be totally mum about this context. If they write this, it will be a big contribution to mathematics, but they are consistent and they keep mum. So even the books keep mum about all kinds of things. And it's really terrible. Okay? Like in Fulton chapter 1, he shows that pullback is surjective on affine bundles. Now any reader, okay, surjective, is it injective? One line is all that it will take to say yes, it is also injective, or we don't prove it here, or it's not known whether it's injective, or see later ... chapter where we'll address this. Nothing is said, and this repeatedly happens. For me, it's a source of frustration and a bit of anger about the way mathematics is taught, written by professional mathematicians. That why they are so violent about it, why they are so stingy about telling us why this is being done and where it is going. Yeah? So when I have this equidimensional scheme and I have a meromorphic function, I want to take its Weyl divisor and show that it's a linear combination of Weyl divisors of usual rational functions on usual varieties. So that's why that equality, algebraic equality applied to this ring gives you that answer. That this cycle is this, and therefore that's what it is. Each one coming from one of the components. This Ri is the restriction to that component defined by Pi. So that is your usual Weyl divisor of a rational function on a variety. So the end result is this cycle is a linear combination, this Weyl divisor of my meromorphic function on a scheme which was not a variety is a linear combination of Weyl divisors of ordinary rational functions on ordinary varieties, those varieties being the irreducible components of that original scheme. Original scheme was of dimension n plus 1 and was equidimensional. So those irreducible components are also of dimension n plus 1, the ordinary varieties, and this meromorphic function restricts to usual rational functions there, non-vanish, invertible becomes non-vanishing, invertible means non-vanishing, and their Weyl divisors in usual sense are there and they add up to that. This is the proof. So let me take a pause. So this is why this happens, that Weyl divisors pull back to something which is rationally equivalent to 0. Okay, so now I want to compare pulling back of Weyl divisors with pulling back of rational functions. That one has to do some cases. So I have two schemes, some morphism of schemes. Okay. It may be an open embedding. Simplest kind of flat morphism may be an open embedding. What happens under open embedding? Now that's very clear. A cycle under open embedding can be restricted. You throw out all those square bracket V, where V does not intersect the open set. Once V intersects the open set, the generic point of V is in that open set. And so you see it. So those are the only ones you keep, throw out the rest. And so that's how you pull back. How do you pull back meromorphic functions to an open set, but meromorphic functions from a sheaf? Why? Non-zero divisors have good localization properties. Why? Associated primes have good localization properties. You know what are associated primes under localization, etc. So primes are well behaved under localization. You know primes in localization are those primes you don't meet S, etc. etc. So open, it is obvious, it's clear from the definitions, it's clear even to me. And so you guys write down the proof if it's, to make doubly sure you understand, it's clear, meaning the proof is 2 lines, 3. Next case is the affine case. This is the case you are going to do with algebra. That if my flat morphism itself came from a flat homomorphism of rings, and those rings were finite type K algebras both, and I have flat homomorphism of those. Under that situation, if I begin with an invertible element of the total quotient ring, because meromorphic functions in the ring context become the total quotient ring, where you have localized the ring A with respect to the set SA of all non-zero divisors. By the way, okay, another aside, I can't resist them. You know how to localize a ring at some subset S, right? Huh? So what is the localization? Localization is a new ring and a homomorphism having a certain universal property. How do you make this localization? It's up to you. Any two constructions will be uniquely isomorphic to each other. That's the universal property. Are there more than one construction? Of course, of course. I mean, who told you to write it A upon B with a line like that? What if I write it A wavy line upon B? Or if I write A and B side by side and make the same equivalence? Said theoretically, they are very different, right? Yeah? You might write something as an ordered pair. I might write it as a 2 by 1 matrix, column matrix. Said theoretically, they are very different sets. But they have the same universal property, and so there is a unique bijection between them commuting with that map from A. Okay? But now, okay, this much, of course, and sometimes one has to emphasize these things, so that things are not physically unique necessarily. The empty set is supposed to be physically unique. This is one of the great superstitions or whatever. Set theory is basically superstition. But sorry, I mean, some things will have to be, censored on this. All right, so, but otherwise, that's why category theory becomes important, that you have to focus on their universal properties and unique up to unique isomorphism. Everything has multiple copies, and sometimes things have automorphisms. Horror. They are not unique up to unique isomorphism. How about algebraic closure of R? Well, there are many algebraic closures which R has. For example, take RT upon the ideal t square plus 1. But you can take Rx upon the ideal x square plus 1. But how about Rx upon the ideal x square plus 2? That will also do. There are so many versions that C has. Now, I have my version of C, you have your version of C, and suppose we agree on our version of R, where again, of course, many versions possible. Is there a unique isomorphism between my version of C and your version of C? And this is the biggest lesson of undergraduate mathematics, that there is not. And that's why there is Galois group. The damn thing has automorphisms, which in this case is Z mod 2. So Galois realized that you can take extension fields, all right, which is the splitting field for something. Yes, any two such will be isomorphic as extensions. Yes, but there will be plenty of isomorphisms possible. In other words, go by one and come back, that's an automorphism. There are plenty of automorphisms possible, and it's important what that group of automorphisms is. Important information is coded in the non-uniqueness of the isomorphism. The automorphism group is very, very important. So set theory based mathematics was ignoring these automorphism groups in all kinds of situations, which is why schemes were replaced by stacks. And so algebraic geometry properly by graduate students should be studied over stacks. And so naturally after this you will ask, how do you do Chow groups and whatnot over stacks, and so on. So these are directions in which people can write theses about various things and so on. So if you are in such areas and looking for thesis problems, there are lots of things done about calculations of Chow groups, done for schemes, interesting schemes. You can ask, oh, then what will be the Chow group for the corresponding stack? Yeah? One of my students in his thesis addressed one such problem. Okay. So, coming back to this. So, automorphisms are very important. And why did I go into that digression? At what point? Hello? No, too entertaining. All right. So, when I am localizing, there are no automorphisms. It's unique up to unique isomorphism. My next question. I all the time see that, people localize with respect to a multiplicatively closed subset which doesn't contain 0. Why this? All that you want is a universal homomorphism to somewhere where everything in S is going to become a unit. Who says S should be closed under multiplication? Who says 0 shouldn't be there in S? Okay, what if 0 is in S? What happens? You get the 0 ring. Okay, what's the 0 ring? 1 is equal to 0, no problem. Okay, so, and why should S be closed under multiplication? I see no reason whatsoever. So why are such things written in the basic algebra books? No idea. Anyway, so that was about localization. I talked about localization, so I wanted to point out that localization is an abstract concept, unique up to unique isomorphism, and has nothing to do with multiplicative closed. However, the set of non-zero divisors is multiplicatively closed. And the units in the total quotient rings can be written as non-zero divisor upon non-zero divisor, because the other way around is again a non-zero divisor upon non-zero divisor. Okay? So you know how these units in meromorphic functions look. Alright, so coming back here, in affine case I have to prove this, and that is all simple algebra, which is already done. This equal to this equal to this equal to this, therefore this equal to this, and I can once again repeat all this, but there is no point. It's written in your notes, it's written in the slides, and you can read here. So I'll take it that the algebraic part is proved. It's easy, simple algebra. What is more important is for you to understand what is happening. Once that is done, let's come to the general case. The general case goes like this. So let me draw some kind of a picture. So I am going from x to y, and this is not affine, this is not affine. I want to study it affine locally. But I am not just studying one scheme, I am studying a morphism. So if I just take some affine open curve, where it's going I have no control. So I should begin with an affine open curve here, spec bi, or whatever it is called, bi. And this is f. Take its inverse image. This is f inverse of spec bi. This need not be affine, but it is covered by affines, and that's spec a ij, one additional index. It may run to different lengths depending upon different such neighborhoods. And now this spec aij is mapping into spec bi. So this part is given by bi to aij. So this part you understand well, this pullback. That is the algebra case. And overall now I want to understand in terms of such. So I need some kind of a diagram. And the diagram will look like, so I have these non-vanishing meromorphic functions on x, I have these non-vanishing meromorphic functions, or invertible meromorphic functions on y, I have this pullback in the other direction. I can go by Weil divisors to this z, whatever it was. What numbers I given, I don't know. Let me call this n dimensional. This is n plus d, or perhaps n, okay, doesn't matter. Then this will be n plus d minus 1 of x, okay, and this will be z n minus 1 of y, and here's the flat pullback. But in between, there is this spec aij, okay, and there is k star of that. So this is q of a ij. No, aij was on the other side, is it? Or those were b? B. Okay. So this will be q of bj, one of those guys, and there is this f upper sharp, same notation. I don't increase the notation. And then there is this z n plus d minus 1 of spec aij, and this f upper star of z n minus 1 of spec bi, and there is this taking the Weil divisor. These maps are taking the Weil divisor. I want to show this commutes, and algebraically I have shown this commutes, and this is an open inclusion, you see. Spec aij into spec x is an open inclusion, and I am pulling back by this open inclusion. And so, since I showed that pulling back by open inclusion, everything works nicely, this commutes, and so on. So, this is the pullback, this is the pullback. I know this commutes, I want to know this whole thing commutes, and by commutativity of the various diagrams, I know that I can diagram chase all around it and end up here in two different ways. I can, or rather, start from here and end up here in two different ways. I can pull it here, pull back the meromorphic function, pull it back to this total quotient ring, and then take the well divisor. But this I can do this way. So this comes like this. So this whole thing like this is this. Okay? But this is this. So that is the same as going here. But here, now this one commutes. So that is going here. But here is the same as here by this open inclusion. And so on. So finally, this here is, because this commutes, again open inclusion, flat cycles, is this, and this. So the way of going like this is the way of going like this. And the way of going like this pulls back the meromorphic function, takes its well divisor, and this restricts the well divisor to this open set. So pull back the rational function to a meromorphic function, or pull back this may already be a meromorphic function, this may be a scheme. Pull back the invertible meromorphic function, takes its well divisor and restrict it to the open set spec AI, is the same as take the well divisor at the level of Y, pull it back, flat pullback of cycles, and restrict it to the open set. These two are going to be the same for each one of these open sets. So these two cycles look locally the same, and cycles form a sheaf. So if there are two globally defined sections and I want to check they are equal, I only have to check them locally. QED? Okay. So that's the completion of the proof. That the variety V, so I want to show V pure dimension plus 1 schematic inverse H pure scheme. I want to do all this for V. When I do all this for V, I show that my basic defining equivalences for rational equivalence become rational equivalences. And so it factors through Chow group. So this is the proof. I have explained the proof, the various ideas, how it links to algebra, and why that kind of algebra is what one needs. All such things have been explained. So we have done flat pullback. And so this completes our treatment of flat pullback, which went from slide 3.8 to 5.6, quite a lengthy one. And the proof in Fulton is tricky but has some independently useful ingredients, which I am going to do. Proper push forward. And proper push forward we have already done. He needs it. In proving this, he needs proper push forward, which we never did. And push, pull, push, he needs in proving this in his tricky proof. And he needs how to represent rational functions via morphisms to P1 in his proof. And I don't need any of those things. And you know, he doesn't explain why he is doing such a tricky proof. Perhaps he wanted those ingredients because they are extremely important in what follows, and he took the opportunity to use them to give a tricky proof. What? Or to him, there's nothing tricky in this, pretty straightforward. What are you fussing about, you moron? You call my proof tricky proof? It's no straightforward proof. Okay, yes sir, my fault. Now, so let's now go to pull, push, push, pull. So this is the proposition 7.2 in Fulton. Take a proper morphism. This is the proper morphism. And take a flat morphism of relatively constant dimension. And simple algebraic, geometric, whatever properties you call them, show that base change of proper is proper. And base change of flat is flat. So you can view this as the base change of this via this base morphism. Or you can view this morphism as the base change of this morphism done via this morphism of the basis. So the same Cartesian diagram of fiber product you can view two different ways. And so correspondingly this is flat and this is proper. And now you can do this composition, that composition either way, and they commute. This is the shoes socks example. Okay. Kaise bhi order mein dalo, it's the same. So the proof in Fulton is sketchy, but I have written it in great detail in section 6.1 of my notes. Okay. The notes are there on the home page, or they were also emailed to them, both.
Email to them certainly.
Achha, but they are there on the a syllabus page of the NCM workshop. I say this on camera because there may be spectators later who watch the videos, I hope. And then they will keep seeing this reference to notes. So they are there on the home page of NCM ATM schools, this one. Let's hope they survive there. Alright, so proof is explained there. And the corollary to this is what? That because these things preserve rational equivalence, which we already proved, that flat and proper push forward, flat pull back, all preserve rational equivalence. And because these are the same at the level of cycles, they are the same at the level of Chow groups. There is no problem about being same at the level of Chow groups, which obviously they are, if at all they descend to Chow groups. Okay? So I have some homomorphism x to y of groups, say, and x has a quotient group and y has a quotient group. And if at all it factors uniquely. So being same there is immediate consequence of being same here, but going down is the point, and that is done because we proved that rational equivalence is preserved by proper push forwards and flat pullbacks. Okay? So you only have to prove this at the level of cycles in order to get this corollary. This corollary is what we really want. Of course, the cycle level statement is also very useful. So let's get it. So again, one can make cases. I think either Amit or Chetan, one of them, commented that we repeatedly deal with the situation where we can reduce to that thing itself being a variety, or this thing itself just being the inverse image, same variety, etc., etc. These kinds of reductions I have also been doing all the time in this proof. Okay? So by this kind of reductions, you can reduce it to one most important case, everything else very easy. And the most important case is this. This is the case when x to y is a proper surjective morphism varieties of the same dimension. Okay? So this and this are varieties of the same dimension. This is a proper surjective map. This is the interesting case. Otherwise, this is pretty easy. And this case quickly reduces to algebra. So I can take the function fields now, both are varieties. And so really, I want to know whether the coefficient of that itself is occurring with the same multiplicity, whatever, of some cycle in this. So I take some cycle. See, it's all going from here to here, right? So given some subvariety here of the appropriate dimension, I want to know its coefficients for this and that are the same. So first of all, and those varieties are mapping there surjectively. It's something is happening over the quotient field there. So I just go to the generic points and replace them by their fields. So I replace x by the spec of Rx, I replace y by the spec of Ry, and base change now. Now the problem, and it's no problem, is these are not finite type over small k, are they? Of course not. So we are working now in commutative algebra, and these are not any nice k algebra, finite type k algebra stuff. This is commutative algebra, very simple in its own right. I got a field extension, and each irreducible component y double prime of y dominates this. So the generic point maps to a generic point, and so that local ring, which is Artin local ring, this is an algebra over this. So y prime is replaced by spec of an Artin local ring over this field. This is replaced by a field, this is replaced by an extension field, this is replaced by Artin local algebra over that field, and this is replaced by the tensor product. What is base change? Tensor product, which may not be local anymore. Okay, which is Artin all right, because this after all is a finite extension of fields. This is also finite. So that's Artin but not local. So B is finite over A, hence an Artin ring may not. I have even written it there, I didn't remember. So this equality holds if the numerical coefficients of each y prime are equal on the two sides. And so this is an algebraic statement now about a finite extension of fields and an Artin ring over this and tensor product with the extension. So this statement is a very simple exercise, so I am not writing the proof here. Let L by K be a finite extension of fields, let A be a local K algebra, not necessarily a finite type over K, and this is the tensor product. So the single maximal ideal below has become a finitely many maximal ideals upstairs, and then by that degree you multiply the length of K, and that is going to be equal to this. And this equality tells you that the numerical quotient of that irreducible component in y prime is the same either way. This is what this equality geometrically means. Translate resolutely, draw a picture. Oh, this A is here, this is this thickness, this is this, so this is saying this here. Yeah, this is the kind of algebra geometry translations you have to do. Being algebraic geometers, this is one of the pleasures of being an algebraic geometer, that this is nice translation. There's another thing in algebraic geometry where you convert things into partial differential equations and Hodge theory. Yeah? And then that also you should kind of learn, and yeah, I know not everything is easy for everybody. Some people find that easy and find the quantitative algebra difficult. For some people, the complex analysis is easy. All kinds of, and not functional analysis, anything is possible. Okay, so I am not going to spend more time on this, and so push-pull is equal to push-pull. No, pull-push is equal to push-pull. Via this most important equal dimensional case, rest of it is easy. Yeah. Again, exercise for you, write down the full proof yourself. Otherwise, see the notes where things are written. Now we come to the open-closed exact sequence. This is the last slide of today's lecture. So suppose I have a closed subscheme of a scheme, and I take the complementary open subscheme. Then the following sequence is exact. And you can begin with the open subscheme and take the complementary closed subset, and no need to ask what is its scheme structure, as I commented before. Give it the reduced one, no problem. Or any. The claim is this sequence is exact. See, often you want to decompose spaces in terms of spaces that you know. There's projective space, and then it has a lower dimensional projective, one dimensional less, linearly sitting inside, and the complement is affine space. There are all such ways of decomposing things in terms of what you already know, what is easier. Lower dimensional projective space should be easier, and affine should be easier, and then you approach projective space. There are lots of interesting varieties which have such quote-unquote cellular decompositions. Yeah. So this is a very, very important statement to be applied to approach something in terms of simpler components. And we will powerfully use it in what follows, or Amit will use it. So the claim is this is exact. Now, any question? Obvious question, hey, this one is not injective. That's the obvious question. Answer is no, it's not. Okay? And that's where you want to know, then what can I naturally put on this side, this side, this side. And those are the higher Chow groups. That's that direction. Spencer block. Okay. Now, how to prove it? So let's look at the level of cycles. Each is a quotient of cycles. So you see what's happening at the level of cycles. So at the level of cycles, the points of that constants degree n partition into points which are in U and points which are in Y. Meaning closed subvarieties of dimension n either have non-empty intersection with U or are wholly contained in Y. And so the cycle group immediately decomposes as a direct sum. At the cycle level, why just short exact sequence? It's a direct sum. Not just right exact, but even short exact, but not just short exact. Split naturally. It's a direct sum. See? So at the level of cycles, it's very nice. What happens is something funny. You see, I might have something in Y which is not rationally equivalent to 0. There is no one higher dimensional variety there whose Weyl divisor is this cycle or some of such things. But that one dimensional higher variety might go outside Y, might make an excursion into U and come back. And then where that rational function vanishes is in Y. Perhaps it also vanishes outside Y, but it's after all the sum of such things, and there may be cancellations, finally leaving nothing outside Y. So it can very well be the case that I have cycle in Y, which is rationally equivalent to 0 in X, but not in Y, because the varieties involved and the rational functions involved in making it 0 are not contained in Y, they are contained in X. And whatever extra pole zeros they have outside Y are getting cancelled. Maybe they are just not there. And so leaving you with this being. So that is why, that's the moral reason why this, you should expect to have kernel. Such a thing is entirely possible. Yeah. Okay, that is the only point to be explained. The rest of it is pretty obvious. So do all this calculus and you see why it is, this much is true. The real question was why not that I explained. Why this much? Just technique. Now see, write the cycle. So if something goes to 0 there, I want to show it comes from here. Well, I know it at the level of cycles itself. Huh? But if something goes to 0, meaning it's rationally equivalent to 0 there, now I want to know something. So all these are pretty simple manipulations. Where the varieties here are to be converted into varieties here. How do I do that? Closure. Rational functions on those have to be converted into rational functions here. How? But rational functions are the same, right? Rational functions on an open set are the same as rational functions on all of it. So there is easy doing this back and forth at the level of nuts and bolts. And so, as this map J star is surjective at the level of cycles and this is 0, well, so only thing remains is if something there becomes rationally equivalent to 0, then it comes from here. That's the only thing to be shown. And that proof is very simple. I don't know, when people teach algebra, and I already confessed I have not been to classrooms. Not strictly true, I have been to higher level classrooms. But when they teach algebra, do they really go through all such? Meaning the teacher goes to the board and writes one equation, then another equation, then another one, says that, yeah, this is how algebra is taught? Killer, man. I mean, I would, yeah, that's why I didn't go to classes. Okay, so, no, algebra doesn't work as a spectator sport. You understand the idea and then you sit down and do it yourself. Get stuck and then consult again. Okay, so this is the open, close, right exact sequence. So any questions?